Okay, well, it is fantastic to be here today and to see such a big audience, and I would think this really isn't because of my reputation, it's because of some fantastic organisation to really advertise this talk. So, fantastic job, everyone. Yes, so what I've been asked to do really is to introduce some of the main topics that came out of the past IPCC report. We had a 5-day meeting in Stockholm, in fact, about 10 days ago, and at that meeting in Stockholm, the report was eventually approved by 195 countries that call themselves this Intergovernmental Panel for Climate Change. So, what I'm going to talk about briefly, I'm first going to give a bit of an introduction to the IPCC for those people that don't really know what it does, and I am probably one of those that don't know what it does. So I will talk about that, and I will then introduce some of my own particular highlights from the document. It's a document that goes over 2,000 pages, so I can't show you everything and you'll be fast asleep before I got on to page 10. But I'm going to show you my own things from the report, and then hopefully we have lots of time to ask questions afterwards. So, firstly, what is the IPCC? And this is a nice infographic that's provided by the Business Institute at the University of Cambridge. And this is how it ought to work. It probably doesn't work this way. But and the Intergovernmental Panel for Climate Change is really what it says. It's 195 different countries, and what the countries do, they get together once every 5 years or once every 6 years, and these countries decide to commission a whole set of quite comprehensive reports, and they basically say to the scientific community, okay, you have to write a report on the current state of understanding of the climate, and they then go and select scientists from their own countries to spend a 3 or 4 year time period producing these very big fat documents. And then at the end of this process, the Intergovernmental Panel does come back together, and then it officially approves these documents, okay? And in particular, the summary for policy makers at the beginning of this document, that is approved word for word, basically, by all. This time we had 110 different countries there, so we had 110 different country delegations there, and they were all picking different words and saying, you could write that little paragraph that way and this way. So it took a very long time, basically. but at the end of 4 or 5 days, we did finally approve the document. But that isn't the end of the whole point. The whole point is to write a document that policy relevant, but not particular policy prescriptive. So we're not trying to tell politicians what they ought to be doing. We're just trying to outline the consequences of either their different actions or their inactions. And so then these reports get disseminated. And in fact, I would just reflect on this for a bit, because one of the most interesting things is that I do think this assessment is completely unique. There is no other field, in fact, anywhere, I think, that gets asked to comprehensively assess its own subject from time to time. And what makes it so interesting is this intergovernmental connection, and the reason behind that is supposed to be, in fact, that Margaret Thatcher and Ronald Reagan were two of the people that really supported the setting up of the IPCC, and they decided that they just didn't want this to be one more UN type thing going on, because the UN was really bad and terrible and it didn't do the right thing at all. So because they were against that, they did say, we want government oversight of this document. So, and they put that government oversight there. What they were thinking, the story I've heard, is that they wanted to restrict its influence, perhaps. But I would say that I think exactly the opposite has occurred, and because it is this intergovernmental panel, the governments do really give this report a lot of attention. So they do take care of every single word in this summary for policymakers, and it's very interesting the way that works. Yeah, okay, and I'm quite happy to talk about the ins and outs of the IPCC afterwards, but I think we get on now with what's in the actual report. Yeah, that's not really 7:30, is it now? It is. Oh God! What time did we start?
Oh, you started.
Okay, good. Sorry. Okay. I don't make sure I keep on time. That's all. I want to talk about the observations at the beginning. Okay, some of the observations that really underpin our understanding of climate change. And the first set of observations I want to talk about today are really the ones that underpin the analysis of the Earth's energy budget, okay? So what I first say on this diagram here are the very obvious observations of the globally average surface temperature change through time. This begins about 150 years ago, and it comes up to 2012, 12, okay? And you can have a look at the surface temperature change, and you can look at this and see that this temperature has gone up by about 0.8 degrees over this time. You can also have a look at the increase, and you can see that this increase is certainly not uniform with time. So it doesn't go up completely straightforwardly with time, but what is obvious is if you to split this up into the average temperature over different decades, which is what you see on this diagram, where you see the very last decade and the 2 decades before that have been consistently warmer than each other. And if you look at these 3 decades, they are the warmest decades in our entire observational data set we have got, okay? They're very warm, and in fact it is this plot down here which I think is perhaps the most interesting, one of the most interesting ones, and this did show the different geographical pattern of the surface temperature changes through time. This shows trends from 1901. We don't have observations everywhere, so for this time we don't have observations over parts of Antarctica and parts of Africa for this time period, but we do pretty much have good global coverage of temperature, and you can see that pretty much everywhere the Earth's surface is increased, and particularly if you look at places like Siberia, they've gone up by about 2.5 degrees over this time period, okay? So they've really increased their surface temperature. And there's really only this one part of the world, in fact, in the middle of the North Atlantic that is cooled over this time. And we understand this cooling. But apart from that one particular part, the rest of the Earth's surface is really warmed up. And what comes out really obviously from this is that it isn't just this increase in the Earth's surface temperature we're talking about at this time. You can look at changes in northern hemisphere snow. You can look at trends in Arctic ice. You can look at trends in the ocean heat content. So this is the top 2 kilometers of the ocean. You can see the temperature that have gone up through time, and you can probably see that over a 100-year time period we've had this increase in sea level that has really gone up pretty consistently through time. So basically, all of this entire set of observations do really point us to the conclusion that the whole Earth has been really absorbing a lot of energy over all this time period, okay? So the whole Earth has been really soaking up a lot of energy over all this time. Yeah, and I just wanted to highlight, in fact, one of the brand new observational records we have got, in fact, and these are these really cool floats within the ocean. They had begun to be deployed about 2002, and we now have over 3.5 thousand of these really cool floats, okay? And what these floats do, they descend to about 2 kilometers within the ocean, and then over a 10-day time period, they gradually come back up to the top. And during that time, they record the salinity and the temperature through time, and they come back up, and then they transmit back to the ground. So for the whole time then, and what the 3,000 boys do is really give us an unprecedented amount of detail about what is going on within the entire ocean, and they're really absolutely fantastic. And so we can really, because of them, we can really say with a good degree of authority that the entire ocean has really been heating up. So we are certain then that the Earth has been really absorbing much more energy over this time, but it becomes much more complicated when we talk about rainfall and precipitation and perhaps changes to the hydrological cycle. And in fact, this was a picture that we didn't put in the summary, but we did end up putting it in the final document at the insistence of the governments in that, because the governments are particularly interested in precipitation, okay, because that affects a lot of what we do basically. But we were saying to them, oh, we really can't do precipitation very well, we don't have good observations, and we don't have good observational data set, we can't really talk about it with much authority. But they do say, okay, but we still want you to tell us what you can about precipitation. So here is a plot of what we ended up with, basically. So this, see on here, you can see these are trends in precipitation, and just look at trends now from 1951, and you can see that a lot, well, we don't have good information for, but there are some parts of, well, where perhaps we are beginning to get a statistically significant change in precipitation, particularly northern European countries tend to be getting wetter, and perhaps there's some evidence of a decrease in precipitation around the Mediterranean and also over West Africa. And in fact, we are beginning to, so we don't have good observations of precipitation. We, in fact, are beginning to get more of a conceptual understanding of what's going on. So we have some degree of confidence that we will get more intense rainfall, basically. So when it storm, it will be at about 5 or 10% more intense than it used to be, basically. So it increased about 5 or 10% more intense per degree of surface temperature increase. And we do have the general idea that parts of where we do have heavy rainfall, we expect them to get an increase in rainfall over time, and parts of the world that are currently deserts like the Sahara, perhaps we expect rainfall to decrease even from what's there currently. But statements like that are, in fact, they aren't ubiquitous now. We thought that was more of a general statement last time, but that doesn't really hold together perfectly. And in fact, some of the work done by Doug Parker and people like that, in fact, do indicate that really trying to predict rainfall over places like West Africa can really be a very hard thing to do, in fact, and we don't have a very good understanding of what's going on. And it's quite interesting, before in the last report we were making very confident ideas about changes to droughts, but we do think we overestimated our confidence, and it's probably pretty unpredictable in fact. And perhaps the one part of the world where we can say with some certainty that there has been an increase in droughts is only really around the Mediterranean, and we expect that to increase in fact through time. Yeah, okay then, let's go on. I want to talk now in fact about one of the most interesting things to my own personal research, which is what is going on with the Earth's energy budget, okay? Sorry, yeah, so this is a diagram that I was responsible for at the time of the last assessment report, and this diagram does try and look at all the different quantities that do cause the Earth temperature to change, okay? So we try and look at the top of the diagram, we try and classify probably the biggest effectors from carbon dioxide, but we also responsible for a lot of other possible effects. And we have some of these effects we expect to increase the Earth's surface temperature, but we also do things like emit some more particulates into the atmosphere, and we have pollution, and we expect these to be cooling. But if you put all these terms together, we expect them to provide a strong warming. But if you look at this, there really was quite a lot of uncertainty. So it's interesting to look at the way the diagram had changed. And this is the new diagram, and it's really complicated, the first thing to look at it. A whole lot more things going on. What the hell is this? So anyway, and I will not go through this diagram in detail, but I just wanted to point out some of the key features on this diagram, and this is the rate of forcing, or this energy change input to the Earth has really gone up by the chromatographic greenhouse gases, principally carbon dioxide, methane and nitrous oxide. They're concentration in the atmosphere has all really gone up quite significantly, and this increase in the greenhouse gases has really given an extra 0.4 watts of energy per meter squared of the Earth, okay? And perhaps 0.4 watts of energy doesn't really sound like an awful lot when compared to a 100-watt light bulb, but just think about a 0.4 watt meter squared light bulb on every single meter squared of the Earth's surface. So that really does add up to quite a lot of energy. So that increased by 0.4 watts per meter squared. The other big thing that has occurred, in fact, is that this estimate of all these different cooling terms is one of the most uncertain aspects of what's been happening to the Earth's surface temperature, and there's a lot of work been done on this. So an awful lot more work has been done over the past 5 or 6 years, and over the 6 years of work, people are really beginning to at least understand the uncertainty behind these terms and understand all the possible indirect effects of these particulates. So these particles, not only do they reflect sunlight in the atmosphere, they can also alter the property of clouds. So, and we estimate, when we do take all these terms together, that this cooling effect is really not as big as we thought it was, basically, okay? So we have changed the estimate from offsetting a 1.2 watt meter squared to now only 0.9 watt meter squared of cooling. And quite importantly too, we have revised the uncertainty estimate of this. So we have managed to constrain it a bit more than we were. And just and sort of because of these two revisions, we have really increased our estimate of the amount of energy that we have been putting into the Earth over the last 150 years, okay? So that estimate has gone up from about 1.6 watts per meter squared to now up to 2.3, okay? So and that is quite a big change, in fact, in the amount of energy we think we are putting into every square meter of the Earth. So what I want to talk through now are what are the implications of that extra watts per square meter we're putting into the Earth. So what we show on this diagram are all these different components that we think caused the Earth's surface temperature to change, and have altered the energy budget of the Earth. So we do have this purple line on this one is the extra energy input from greenhouse gases, and we estimate over this time period they've put in 1,200 times 10 to the 21 joules over the last 30 years, okay? So huge. But we have things that are called the Earth to cool, and particularly on this green curve, this is the effect of volcanoes. We do have big volcanic eruptions go off from time to time, and when we do have these volcanic eruptions, they do act to remove energy, okay? So basically, if you put all these terms together, you end up with this black line on this diagram. And so this says the black line on the diagram is what we think is the extra energy ending up in the Earth, okay? And we just transfer that black line on this side of the diagram across to this side of the diagram. And this side of the diagram does tell you about the different responses, okay? So the Earth is taking up that extra 2.2, 2.3 watt per meter squared of energy, and that goes in this black line, and it's the black line, and we do then have quite a lot of that energy does really end up going into the ocean, okay? So a lot of this extra energy to go into the ocean, and we have a little bit does go into the ice, and a little bit does go into vegetation and things. So we can put all these terms together, and we end up with this blue line on this diagram, okay? So this is the energy that the Earth is absorbing, okay? So this is the energy that's coming in to the Earth, and then this is the energy that the Earth is still absorbing. But of course, you cannot create and destroy energy, so that does mean that the difference between this blue line and the black line on here does have to be the extra energy going back out into outer space. So this is the Earth basically responding by putting a whole lot of energy back out, extra energy back out into space. But here's the crunch, that we don't really know what that is. And because the amount of energy the Earth puts back out into outer space does depend on probably the most frustrating parameter we talk about in my field of work, which is this weird thing called the equilibrium climate sensitivity. And this equilibrium climate sensitivity just tells us what we expect the surface temperature of the Earth to be if you were to double the amount of carbon dioxide, okay? And we have really, ever since we first began our climate change theoretical work, we tried to determine what this surface temperature change for doubling of carbon dioxide would be, and we pinned it down perhaps to somewhere between 1.5 degrees to 4.5 degrees. But frustratingly, even after 25, 30, 40 years of research, we don't seem to have got much closer to it than that. We're still left with that stupid span, and we can't pin it down. But So what's interesting on this particular diagram is to try and compare the Earth, these equilibrium climate sensitivity responses to what fits best with the black line, basically. So you ought to be able to pick whatever equilibrium climate sensitivity does really get you back up to this black line on the diagram to conserve energy, okay? But and you can see that if you had a sensitivity of 1.5 degrees, you would be putting too much energy back out into space, so that's probably too big. But if you have a sensitivity of 3 degrees or 4.5 degrees, perhaps you can't putting enough energy back out of space. So this does perhaps suggest that the equilibrium climate sensitivity would be somewhere between 1.5 and 3 degrees. But and this is really interesting that so a lot of people, if you look in the popular press and thing, they've been speculating that because the Earth's temperature hasn't really warmed up, particularly over the last 15 years, that to tell us that this equilibrium climate sensitivity is big. But in fact, that's not an accurate description of what's going on. In fact, what is an accurate description is that because we have really revised the amount of energy that's coming into the Earth, we've revised that estimate. We've increased it considerably. Because we've increased it considerably, that does suggest that perhaps our estimate of equilibrium climate sensitivity isn't so big as it once was. We once speculated it was. But I want to say too that in fact this Earth energy budget term is just one of the lines of evidence for this equilibrium climate sensitivity, okay? I dramatise. So that is this particular line of evidence, but we have a whole lot of other ones in fact too, and they don't all give a consistent picture of what the equilibrium climate sensitivity should be. So we do still come up, of course, with this same frame we've always have got, and we haven't been able to improve on it, unfortunately. So we're still left up with between 1.5 and 4.5 degrees. But I think one quite nice fundamental bit of work that was part of the responsibility that I did have, in fact, looking at what is the role of clouds, because this is something that has been speculated about for a long time, basically, and we have some degree of confidence, that a lot of the cloud feedbacks are positive, This says that when cloud change in response to a surface temperature change, they amplify the natural surface temperature response. So the one thing that principally occurs is that as you increase the surface temperature, the altitude of the clouds go up, and this increase in altitude does make the clouds absorb more infrared radiation, so they act like greenhouse gas, and they actually increase the surface temperature change. Okay, I just want to briefly talk about the last 15-year time period and what's been going on. So I'm probably going on too slowly. I'll try and speed up a bit now, because by now you're all experts. Okay, so this is what I want to say now. I want to talk about, we've seen a big increase, but what has been going on over the last 15-year time period. Earth's surface temperature has not seemed to be going up, and that's very interesting. But the big thing is that, yes, the Earth's surface temperature is not going up, but we really do see a lot of other evidence over this time period of the Earth absorbing more energy, and the climate is still changing, okay? So we have the sea ice melting, the ocean taking up heat, and the sea level going up. So this is just the Earth's surface temperature we're talking about. Climate change isn't stopping. But the reason why it's so interesting is that these state-of-the-art computer simulations we have got of the Earth temperature change, these are shown here at all the different colours. These are all the computer simulations of the historical temperature, okay, and the black line on here are observations of surface temperature. You can see that these computer simulations do a really pretty good job of reproducing the surface temperatures, but they certainly do not do a good job for this past 15-year time period, okay? They tend to really have too much increase in the surface temperature. And that makes everyone very interested, of course. So there are three things we want to try and answer with this. What has been the principal cause of this reduced trend in the surface temperature? Other thing is, why aren't our climate models able to reproduce it, okay? What's going on? And the fact is they probably weren't designed to reproduce it, because they all started a very long time ago. They all started with the ocean back as it was in the 19th century, okay? So they wouldn't be expected to get all the little ups and downs and all the fluctuations in exactly the same time that we observed them to occur. But if we do begin our computer simulations from the ocean surface temperature during the 90s, they still don't do a good job, particularly, and they still end up warming too much. Yeah, and once we understand what caused it and why our computer model can't reproduce it, we can then go on and think about implications of it for our projections of climate change. Okay, so this just looks at the surface temperature changes over the last 15-year time period, okay? And what this tells us, and this first look at the red line on here, the red line on here are our estimate and the uncertainty estimate of the observed surface temperature trends over this time, okay? And and we see this quite small trend. It's still positive, but it's only just. And then if you look at all the different grey bars on the diagram, these grey bars correspond to 115 or 114 different computer simulations from all world of what the surface temperature was over that 15-year period, and you can see that pretty much only one or two of these simulations to actually get the right one, get it correct. But part of this problem is that we're only looking at a particular time, of course, and if we look at other different times, we can see that we get a different picture from this. If we look at the total trend since the 1950s, okay, the computer projections and the observations do really fit with each other quite convincingly. But if we look at a period from the 1980s, which is this one here, we can see, and in fact we get the opposite effect going on, whereas the computer simulations do or underestimate the observed increase in surface temperature trends. The part of the problem is that we're only focused on a very tiny 15-year time period, and when we talk about climate change in general, we're really more interested in longer time periods. I'll skip that for the sake of argument. So what is part of the reason for this? And this is highlighted in this plot. So this looks now at the things that are causing the Earth temperature to change, okay? So this looks at what the anthropogenic driver of change over different time periods, as shown as these red bars on this diagram, and their different time periods, and then the green ones on here are the natural radiative forcing, and these are changes in the sun and changes to volcanic activity. And what I want to point out to you, that if you just look over the last 15-year time period, we've in fact seen a particularly big minimum in the sun, okay? The sun had a particularly long and big solar minimum in 2008. And that is really the principal cause of why this had contributed to cooling. We've also do have a contribution from 4 or 5 little volcanoes that have been going off too over the last 4 or 5 year time period. So we've had some tiny volcanoes, and we've had this very strong solar minimum term. And that does in fact give us a slight cooling effect, but that cooling effect is not really big enough to account for this slowdown in temperature completely, okay? That probably does just account for about 50% of what's going on. And we think that other 50% is to do with what's going on in the ocean, okay? We do probably think there's some quite peculiar ocean circulation going on, and that ocean circulation is really taking heat out of the surface and distributing it down to the lower part of the ocean. But we only have good ocean temperature measurements down to the first 2 kilometers, and we don't really know what's going on with the ocean beneath that. So it's a bit of speculation, but that we think is occurring. So I just want to talk now about the implications, and I then want to talk about projections, and then we can come to the end. Sorry again, I'll try and speed up even more. So this does briefly capture then, we have the brand new part of the IPCC report, and this talks about our estimate of surface temperature change just out for the next 2 or 3 decades, okay? And what we've had to do for this time is try and revise our estimates from these computer simulations, because they were all forming too intensively over this period. So what we had to do, we've just had to try and re-normalize these computer simulations to this to the 2010 time period, and what we've also done for these, because we think, as we talked before, that perhaps these simulations have too bigger equilibrium climate sensitivity, perhaps. We have just revised them down. We have revised their response to carbon dioxide down by about 10%, okay? Just made quite a, because perhaps they were forming too much than we've observed. And because of those two differences, they do in fact significantly reduce the projected temperature change just for the next 2 decades, okay? This, I talk about in the, this doesn't go beyond that, but just for the next 2 decades, we do not expect the world temperature to go up significantly. Well, it's still going up a bit, but it is not going up as much as we predicted from these computer simulations. Yeah, okay, so I do now want to talk about longer term projections now, okay? And this does now show a plot of these, all these computer simulations now over three different time periods. This is the historical time period. These are the surface temperature change on the axis, and then this is the next 100-year time period out to 2100, and then we've had about 15 or so of these computer simulations have gone all the way out to 2300, okay? And you can basically see on here, and these different colors refer to different economic pathways, okay? So we have this big one at the top, the big red one at the top is sort of, we continue pretty much business as usual, okay? This is burning fossil fuels and just pretty much not really giving much credence to climate change at all, okay? Going forward, and then that compares it to this pathway where we make strong mitigation, okay? And you can you can really see the different contrast in these two pathways going forward. Yeah, but you can also see too that for this 30 or 40 years in the time period, it really doesn't make much of a difference at all which of the economic pathways we particularly pick. But when we get out to 2100, it really does make a very big difference. Yeah, and I ought to get on. I'll just show you one plot, one more plot. This to show, or perhaps I'll show, precipitation changes for European countries. Okay, so and this shows northern Europe up here, and this shows Central European precipitation. And the first thing to look at the diagram is look at them and say there's a lot more variability, okay? So it becomes a lot more difficult to really see a significant change, or it really does take you out to 2100 before you get to see a big significant change in precipitation. But what we do generally expect for the European region, there is an increase in rainfall in the northern parts, and the Mediterranean and the southern part we expect to get, especially by 2100, we expect to get quite significant drying, okay, going on, which is interesting. Yeah, okay, there is one more result I want to talk about, and then that will be it, I promise. Sorry. So, and this, I think, is the most important thing to come out of the document, so please bear with me just for a bit. And this is this concept of cumulative emissions of carbon, okay? And this has really become a new way to think about it all, but it really works, and it's a very good, clear message, I think. And then the basic idea is, let's take a really hypothetical situation, okay, where we just burn fossil fuels for 100 years, and then we suddenly don't do anything. Okay, and we just look in the time series of concentration of carbon dioxide in the atmosphere, and that takes a long time to reduce. Okay, we have some significant amount of carbon dioxide staying in the atmosphere for 400 years, 500 years going on in time. And also, if you look at the surface temperature change, that really only comes down very, very gradually through time. So you can do this for a different amount of carbon, and then if you emit it for another 40 years or 50 years, you do get a pretty much consistent temperature change, different peak temperatures for different amounts of carbon dioxide you pump out. And in fact, what you can do a plot on one axis, which is the total amount of carbon you've emitted into the atmosphere, and on the other axis you can plot this peak surface temperature, okay? Yeah. So and you can also do a plot like this for what's been going on, okay? And this showed exactly the same plot for the historical time series. So this plot does show the historical cumulative emission of carbon dioxide compared to the historical change in surface temperature of the other axis, and you can then continue this going forward with the different economic projections, and you can see that despite the very different projections, these pretty much all go up the same axis, okay? And you get then to 2100, and these different projections have all emitted different amounts of carbon dioxide, and they have reached different surface temperatures. So you end up with this picture of uncertainty, basically. And it's quite interesting to compare this particular situation to this grey bar, which is what you would get if we were just emitting carbon dioxide. But we aren't just emitting carbon dioxide, we emit methane and nitrous oxide and all these other things too. So in fact, the observations of this are slightly on top of what the situation would be if we just were to emit carbon dioxide. But the exciting thing is, you can then actually read off this. We read off the diagram, okay? So you can let's say you don't want to go above 2 degrees, okay? You don't want to go above a 2 degree temperature change, okay? You can read off the diagram what is the total amount of carbon you can emit, and you end up with a 1 trillion tons, basically 1,000 billion. You're allowed to emit 1,000 billion tons if you don't want to go above this 2 degree surface temperature change since pre-industrial times. But because we don't just emit carbon dioxide, this does come down. In fact, it goes up, so this comes down a bit further to about 800 billion tons. So you've got about 800 billion tons. And if you look at what we've currently emitted, we've emitted about 530 billion tons. So, and we're emitting just over 10 billion tons of carbon annually now. So you can see that gives us 25 years, basically. We can continue to emit for 25 years, and then we have to instantly transform our society if we want to try and keep below this 2 degrees of surface temperature change. Yeah, sorry, I've gone way over long, but so I think I'm going to take as my conclusions these 2 statements from the summary for policy makers from the report. This first one was supposed to be the most talked about summary point, but the popular press weren't interested in it at all. So I'm putting it up to hopefully interest you in that. I think it's supposed to tell us all categorically that we are causing the Earth temperature to change and the whole Earth's climate to change. And then the other conclusion is that because we've emitted all the carbon dioxide, we set ourselves up with a very long-term commitment to climate change going forward in time. Okay, I'm going to stop there, and I'm going to take questions. I'm sorry I've gone on way too long, everyone.
So thank you, Piers. I think the introductions went on too long. I think it was good to hear that, and it's really good to hear, directly from the horse's mouth, and also get the personal perspective on this problem. So I think maybe we can have time for a few questions, maybe sort of 5 minutes or so, and then Piers is going to stay around for rather more kind of informal questions after that. So if people need to get away, then they can do that after a few.
Yeah, but don't let us stay. You want to go, just go.
Well, yeah. So we can take a couple of questions then. So there's one back here.
Why is thanks very much, it's a great talk. Why is the uncertainty in the natural radiative forcing for 1984 to 1998 so relatively great compared with the neighbouring time period?
Yeah, that's very interesting, because we had a really one or two really big volcanic eruptions. We had El Chichon and we had Mount Pinatubo, and these big volcanic eruptions, we think we can quantify the energy or the forcing from them within about 30% or so, but because they were so huge, that does contribute, that 30% uncertainty does give you quite a wide error bar.
Following up on that, if volcanoes have such a large impact, do they go into your future predictions as well?
No, and so they're all slightly overestimated. Oh, well, that's not entirely true. There is one of these climate simulations does include them. The rest of them do not. So they do all assume there aren't going to be any more volcanoes, so that is incorrect. So they do slightly overcook it. Yeah, so they do form a bit more than we would expect, but they do not have volcanoes.
Yeah, methane, rising temperatures lead to more methane loss from the permafrost.
Yeah.
And also potential deep sea methane. Have you factored that in? What are the consequences if we have sudden more release of methane from the permafrost areas? The second question, as a counter to that, as ocean temperatures will rise, plant growth, algae growth will increase. That will absorb CO2. How is that being factored in?
The answer in, I could go back a slide or two maybe. Oh, I've had the answer is no, but they are considered. They're considered that we could have these big feedbacks from the carbon cycle, methane from permafrost and things, but the fact is we can't say for certain which direction they would carry in. So we did it in the report last time. In the report report we wrote last time, we did speculate there could be a big dieback of the Amazon. So, and in fact, if you did look at our surface temperature change estimates for 2100 from this report, which are the numbers here, compared to the past report, we did talk about the possibility of really getting a really big temperature change, 2100 from the dieback of the Amazon. But in fact, we don't do that this current time because we think the different carbon cycle effects and the permafrost effects, they could be countering each other. We don't know how big they are. It's a big uncertainty. So we don't currently try and put them into these simulations, but we always think that they could be going on in the back of our heads, but we haven't found a way to put them in yet.
our climate's very much affected by the Gulf Stream and also the jet stream. I gather that they're likely to weaken. What's your views on that?
We have more certainty of the Gulf Stream weakening. So that definitely has occurred. If you remember that first plot I showed you at the beginning of the talk, I won't go back to it, it's going to take forever, but the one part of the world that hasn't warmed up is just where that Gulf Stream effect is going on. So we can explain that, can we to think that effect will continue and increase, but it won't increase hugely. So the best part of the world to be is probably the UK if you want to avoid. It's the one part of the world that won't really warm up, unfortunately. Yeah, but you're talking about the jet stream one. We have some idea that the jet streams do move more toward the poleward, and perhaps they weaken a bit, but that is not quite so certain.
So we've got one more before we
You make the point that about half of the CO2 warming is offset by anthropogenic aerosol, in broad terms. What would happen if we cleaned up the atmosphere for reasons, for health or whatever, other than climate, or even stop burning carbon? Because the time constant of the aerosols is days and weeks, and that's the carbon dioxide, as you pointed out.
Yeah, well, you could people are really concerned about that for a long time, what they cleaned up aerosol, but it's probably not as big a factor as we first thought it was. We thought we might get a huge increase in temperature change, and it's probably not as big as we thought, but this is what is going on in these different projections. Yeah, okay? So you can see at this particular point where we are today, the effects of methane and nitrous oxide are probably completely countered by aerosol. So that's what we think is going on. And you can see that historically we've been a bit below the carbon dioxide curve because of the aerosol cooling term. But you can see that as we go forward and we do clean up these pollutants, we do end up going above the carbon dioxide line. So yes, so it's because of that aerosol cleanup that we don't have 1,000 billion tons of CO2 to emit. We only have 800 billion tons.
Okay, well thank you. So we do need to come to a close because I know some people have trains and want to catch. So it's very interesting to have these questions. I think Piers will be around for a little bit to answer questions informally. If you want to know more about these kind of subjects, do register for a degree in our university. Things to say about this. So finally, I'll just thank Piers for a very interesting talk.